Well, it's great to be with you again today. We have lots to cover today, so we're going to move along quickly. Let's go ahead and get organized. For materials, you'll need Activity 3.1. That's going to be part of your assignment. Activity 3.4. This is one on heat, terms, but there's a section on heat distribution that you'll want to fill in as much as you can during the lesson, with the exception of number 9. That one will not be covered in our lesson today. On our agenda, we're going to start by reviewing some information on the seasons, then we'll move on to winds and air pressure, and we'll have a little popcorn demonstration and another one if we have time. Our main idea today is that air masses and ocean currents help to explain the uneven spread of heat throughout the Earth. For goals today, you need to be able to explain the basic cause of wind, describe the Coriolis effect on wind direction, locate and describe the horse latitudes and doldrums, and also identify the wind belts on a globe and distinguish their basic characteristics. So that's what we have in store for us today. Let's go ahead and begin with our chapter verse. Read along with me, Genesis 8:22. While the earth remaineth, seed time and harvest, and cold and heat, and summer and winter, and day and night shall not cease. And that's God's promise to us, that we'll always have the seasons. So we're going to start with a review on the seasons. What is the basic cause of seasonal changes? A tilted axis. What else affects the seasons? The angle of the sunlight, whether it's direct or slanted. Okay, do you recall what are the 3 latitude zones? The polar regions, the temperate zones, and the tropics. Which latitude marks the northernmost limit of the sun's direct rays? The southernmost limit? Okay, the northernmost limit is marked by the Tropic of Cancer. Think of the N in Cancer, or just think of them alphabetically. And the southernmost limit is Capricorn. So Cancer comes in the alphabet before Capricorn. That might help you to remember those. Which latitudes mark the polar regions? Okay, you might think of the number or the name, Arctic and Antarctic circles. Which latitude zones have 2 seasons? And what are they, the seasons? Okay, the polar regions have the midnight sun and complete darkness, and the tropics have wet and dry as their 2 seasons. All right, now we're talking mainly today about wind. What is wind? Ever thought about that before? It's just air that is moving, isn't it? And what causes the air to move? Think of a principle that you've probably heard several times in school, and even at home. I've heard it in different places. What does hot air do? You hear it a lot. Hot air rises, right? What causes the air to get hot? The sun. And if hot air rises, what movement do you think cool air makes? It's only logical. If hot air is going to rise, cool air is going to sink. It sinks, doesn't it? And it's this rising and sinking, this heating and cooling of the air that creates what we think of as wind. And this moving air travels in huge masses covering hundreds of miles. And that's your first term you want to know, and I believe this is on your worksheet you'll want to jot down. An air mass is a large area of air that has a similar temperature and moves together. And we know that warm air masses rise while cool air masses sink. And the sharper the difference in the temperature of the air masses, the stronger the winds that are created. For example, hurricanes pack the highest winds, and they have the hottest and the coolest air meeting together. And when the sun heats the air, the molecules become active and spread apart. You've probably learned that in science. And then they begin to rise. And the molecules in cool air become less active, and they get closer together, and they sink. And that's where our popcorn demonstration comes in. I was going to make it with you, but I thought it took about 3 minutes, and we didn't have that much time. But you can see from the popcorn itself what I'm telling you. You don't really need to see the popcorn being popped. So the kernels are going to represent our cold air. These kernels, the molecules are close together, and they're going to weigh more. So I have a little scale here. That's pretty close. I have a little scale here, and I'm going to put in a 1/4 cup of the cold air molecules. These stay really close together. Oops. Helps to pour out the end with a hole in it. Okay, here's a 1/4 cup of our popcorn molecules. I'll put them in, and let's see. They don't weigh much at all. I'm leaning around here. About 2 ounces. All right, now what's going to weigh more, these kernels or our popped kernels? We'll weigh the same amount. This is our cold air, our molecules that are close together. I guess I need a little, I'll just put them on this little napkin here. Our cold air molecules. And we're going to weigh a 1/4 cup of the popped. That's even a little extra. Okay, we'll weigh a 1/4 cup of the popped. It doesn't even move the scale. Scales don't even move for our popped popcorn. So this is the idea to keep in mind. The cold molecules can be represented by our unpopped kernels, which are heavier, and the hot molecules are our popped corn, which expands. So you think of the air molecules getting busier and expanding and being lighter. So they're going to rise, whereas the other ones are heavier and they're going to sink. Now, if you've ever flown a kite or sailed in a boat, you've seen that air has weight, just like our kernels have weight. And even the popped ones have weight, just not as much. Now, though it's invisible, air can exert great pressure, it can push down trees, it can damage houses, and so on. But which do you think exerts more pressure on the earth? The cold air sinking or the hot air rising? Well, it's pretty obvious that it's going to be the hot air rising, isn't it? And in your textbook on page 40, we have a diagram that shows us this. Relatively cool air sinking is going to create high pressure. Relatively warm air rising is going to create a low pressure. So let's remember our air pressure. Low pressure is an air mass with relatively hot rising air, and high pressure is an air mass with relatively cold sinking air. A popular way of stating air pressure is by using the measurements of a barometer. And a barometer is simply an instrument used to measure air pressure. Makes sense, doesn't it? It was actually invented in 1643 by an Italian named Torricelli, and today we still have versions of his mercurial barometer, but most people use the aneroid barometer today. And I have with me here a tube to kind of show you a little demonstration similar to what Torricelli did. Now, he took a tube. It would have been probably about this length. This is a 36-inch tube, and it's very thin, very long, glass tube, and he filled it completely with mercury. Now, mine's not completely filled, and it's not filled with mercury either. Since mercury is a carcinogen, we don't want to use that. I'm just using colored water so you can see it. And yeah, it's closed off on this end, but it's open on this end. This is where I put the water in. And he took his tube filled with mercury, turned it upside down. I probably should use my other hand so I don't get my rings in there. And put it in a container of mercury. And again, I'm just using water. And you can see it's not moving at all. This is not moving at all. And up here, it's going to be too high, but I can put this down. I think I can set it on the floor. There you go. Now you can see probably a little better. Right here is about 6 inches down. The air pressure was high enough to keep the mercury pressed in the tube about 29.9 inches with about 6 empty inches. But the water is lighter than mercury, so this water stays pressed in here all of the way. It stays just pressed up all the way. The mercury is a heavier substance though, and it did fall somewhat. Okay, so that's similar to what Torricelli did to create his barometer. And I have a little diagram. It's a pretty simple principle. I have a little diagram I'll show you that kind of outlines what's happening here. Okay, Torricelli's barometer. We have our sealed tube, obviously not to scale, with the container of mercury. The atmospheric pressure presses down on what's in the container, which is able to keep the mercury pressed up to about 30 inches high. All right, now I thought you might also enjoy seeing an aneroid barometer. These types of barometers use a little metal capsule or box in them that has a vacuum created inside of it, and that makes it sensitive to air pressure. All right, and on this one we can see it's marked in inches, and here we're right at standard, really, 29.9, and it has a little handle here that you can move so you can keep track of whether the pressure is rising or falling. Also, the second row is marked in centimeters, so it's about 76 centimeters now, and it's also has a third row marked in millibars. A lot of them use millibars. Bar is actually the metric unit for measuring pressure, and it's about, I don't know, it's hard to count these little ones without getting my head in your way, but about 10, looks like right about 1014 1014 millibars, okay? And that's what people use today. It's more compact, it's more convenient, and it's mercury free. So regardless of what type of barometer you use, standard atmospheric pressure is about 29.9 inches, so we're pretty close, 76 centimeters, or with millibars you can be even more precise, 1,013 and 2/10 millibars. So it rarely moves above 31 inches or below 29 inches. And this has from 28, a little below 28 inches up to a little over 30. So it doesn't need to be any higher or lower because the air pressure stays pretty constant. Now, just as the atmospheric pressure does remain somewhat constant with slight variations, the winds on the earth follow a constant pattern as well. And in Scripture we read, "The wind goeth toward the south, and turneth about unto the north. It whirleth about continually, and the wind returneth again according to his circuits." And that's in Ecclesiastes 1:6. And we are going to be looking at some underlying principles of the wind patterns today. We're going to start with a basic pattern caused by the sun's heat, and then we're going to look at 3 factors that alter that pattern. Now, so that's what we're going to be looking at and what the things that you want to keep in mind. I'm going to be using a globe, so I'll go ahead and get our globe up here. Now, there is a warm air mass lying permanently over one of the latitude zones that we talked about in our previous lesson. We only talked about 3, so which zone do you think it's going to be? When we have 3, polar, temperate zones, polar, temperate, or tropics. It's going to be the tropics, isn't it? Yeah, the sun heats the air, and I'm just going to kind of try to show you with my hand what's happening. So try to get where you can see. My hand is going to be the wind. The sun shines at the tropics. It heats the air. What happens to hot air? It rises. So there's the air rising off the surface. And as the warm air rises at the equator, it flows toward the poles. I'm going to stick with mainly the northern hemisphere, but it's mirror. It flows to both poles. Why do you think it flows to the poles? The poles, we have cold air, don't we? And cold air is going to create a high pressure, and down here's a low pressure, so it kind of is a little cycle. It's heating, rising, going to the poles, cooling, causing a high pressure, going back down, heating up again, and it's a cycle just like this. Okay, so that's kind of what's happening with the main pattern. All right, now then we want to talk about our 3 factors that affect that change this pattern. Okay, that's just our basic pattern that we start with, and this pattern is shown in your textbook on page 40. You can see this is what I was trying to show you with my hand. If that's not very helpful, maybe the diagram will help. The air is heated, it rises, it flows to the North Pole where there's a high pressure. It cools, it sinks, the high pressure, cool air flows back to the equator where there's a low pressure, and then it's heated again and rises and so on. Notice it's happening in both hemispheres and all along the globe. We can't show it as well here, but that's what's happening. Now, the sun's effect of warming the air, however, is not the only factor affecting the patterns. The other 3 factors are latitude, the rotation of the Earth, and continents. We're going to start with latitude. Much of the air from the tropics actually cools before it reaches the poles, and this causes our wind to go in 3 types of cells. First of all, our air at the tropics is heated and it rises, creating a low pressure. Then it begins traveling north, and part of the air cools. What's going to happen to it? It's going to sink, right? And it sinks slightly north of the Tropic of Cancer, Tropic of Cancer, around 30 degrees latitude, creating a high pressure. Okay, then this air is going to start back along the surface to the low pressure at the equator. And there's kind of a vacuum there. It's kind of sucked back in. So it's going this direction, toward the south, back up again, and we have a little cycle going. Now the rest of the air is going to continue on toward the poles. Some of the air continuing toward the poles travels north. Since the air cooled here and kind of dropped, some of it travels along the Earth's surface, traveling north, and it meets the cold air from the poles and is forced to rise above that, and it kind of cycles back around. So it's doing a circle. So here we have air coming from the poles, making a circle this direction. Some of it cools, travels along the surface, rises again, and it's making a little pocket of air here. The rest of the air continues all the way to the poles. What's going to happen there? It's going to cool as well, sink, and start traveling back toward the equator. It's going to meet the warm air that we just spoke about, and some of that's going to go in a circle as well. It's going to rise back up and keep going in a little circle. So our big motion is like this, right? That's our basic motion, but we also have little pockets going this way, and this way. They're kind of turning in different directions. And just think, again, in case my hand isn't really as clear for you, there is an illustration of this in your textbook. And this shows the air rising at the equator, creating the low pressure. Some of it cools before it reaches the pole. Some of it curls back around into this vacuum and creates a pocket here going in a circle. All right. Some of it continues on toward the pole, hits the cold pole air, continues really more along the surface of the Earth, rises, and some of it returns. They don't show that part, but it actually makes a little pocket here. They showed the one arrow. We have a pocket of air here. Some of it continues all the way to the poles, cools, and starts back around. All right, so we have a little pocket here. Notice the direction. This one's going this way, so along the surface the wind is actually blowing toward the south. Here's our other pocket along the surface. This wind is actually blowing north. And then this third pocket, this wind is actually blowing south along the surface. So they're blowing in alternate directions, and it's the same in the southern hemisphere. We have a pocket here. Of course, the air's blowing north. We have a pocket here with the air blowing south, and a pocket here with the air blowing north again. So that, the latitude, you can see they're at the same latitudes in the north and the south hemispheres, the northern and southern hemispheres. About 30 degrees latitude is where the first air drops, and about 60 degrees latitude is where the air begins to rise. Okay? Now, a second factor that affects the wind belts is the Earth's rotation. The Coriolis effect makes the wind appear to veer. And it's a little easier to explain with an illustration. So in the following clip that you're going to see, the person in the chair is going to represent our rotating Earth, and the tennis ball that you see kind of swinging in and out is going to represent the wind. Okay, Tanya is rotating counterclockwise to represent the Earth, and the tennis ball is swinging in to represent the wind. And you can see from the overhead view that the tennis ball is coming straight into the picture. It's coming straight toward our rotating. But from her perspective, as you saw there, the tennis ball appeared to veer off to her right, from her perspective of spinning around. And that's what happens with the Coriolis effect. The wind, because of the Earth's rotation, even though the wind is going straight, it's not coming in at us straight, but even though the wind is going north and south, it's going straight, it appears to veer away from us. And this is known as the Coriolis effect. This is the illusion that the wind veers east or west caused by the rotation of the Earth on its axis. And here's what you need to remember. Wind blowing toward the equator always seems to veer west. Wind blowing away from the equator always seems to veer east. Or if you want to think of it another way, if you're following the direction of the wind, it always seems to veer right in the northern hemisphere and left in the southern hemisphere. And I have a diagram here to help illustrate this. Okay, wind coming toward the equator always seems to veer to the west. Wind coming away from the equator always seems to veer to the east. That's one way you can think of it. Or if you want to follow the direction of the wind, let's look at the northern hemisphere. It always veers to the right. We're following the wind, we're veering to the right. This wind is coming from the north, so we flip it over. If we're following the direction of the wind, it's still veering to the right. In the southern hemisphere, the wind is going to veer to the left. If we follow the direction of the wind, it's veering left. And if we follow the direction of the wind here, again, it's still veering left. So the northern hemisphere veers to the right. In the southern hemisphere, it veers to the left. Now, another illustration is to think of tossing a ball to a child on a merry-go-round. If he's spinning around and you toss the ball to him, by the time the ball gets to where he was, he will have spun away from it and he won't be able to catch it. All right? We could also think of a pilot who is starting at the North Pole, and let's say he wants to fly to New York. Kind of hard for you to see New York here, but I like to use this right here. Say he's at the pole and he thinks he's going to fly straight to New York. The Earth actually spins counterclockwise. So he starts, the Earth is spinning. By the time he follows this straight line down, New York is going to have spun away from him. See, I'm following a straight line, but it appears to veer because of the Earth spinning. Okay, it's kind of hard to spin and follow the line at the same time. But I think that gives you the idea of what's happening with the Coriolis effect. The main thing to remember is because of the Earth's rotation, the Coriolis effect, the principle of it is because of the Earth's rotation, the wind seems to veer. All right, so that's the main thing to remember. Now, the Coriolis effect is what's going to help us understand the wind belts. And there's a diagram of the wind belts in your textbook on page 42. You might want to turn to it to have a little closer view of what we're talking about here. All right, now remember our little circles we talked about earlier? Here is our circle near the equator. It's going towards the south and back up, south along the surface and back up. Here's our other circle. It's in between 30 and 60 degrees. It's following north along the surface. And then this one up here, this wind belt, it's following south along the surface. Now, think of our Coriolis principle. If this wind is traveling south, which direction is it going to veer? It's going to veer to the west. See how they have the arrows drawn towards the west? Remember, if it's going toward the equator, it veers towards the west. this air is following north along the surface. It's going to veer to the east or to the right, just like your little Coriolis diagram. This is following south, flowing south, so it's going to veer to the west as well. Notice that the arrows match up with our Coriolis effect. If you're coming down, veering this way, going up, veering that direction. Notice in the northern hemisphere, we follow that pattern. Veering, veering, veering. And it's the same pattern in the southern hemisphere, only the opposite direction. Remember again which direction it's veering in the southern hemisphere, and that is that's the way our arrows are going on this map. Okay, now you want to read carefully over that section to be sure you understand. That's the Coriolis effect that helps us understand these wind belts. Now we do want to remember the names of the wind belts. Trade winds are the common northeasterly winds that blow over the tropics. The westerlies are the prevailing winds of the middle latitudes. They blow from the west, not to the west. And the easterlies are the prevailing winds of the polar regions or the high latitudes. Now there are also some areas of calm between the wind belts that have special names, and we want to remember them as well. They're the horse latitudes and the doldrums. Back to our page 42, well, let's try to get a little better look maybe just at the northern hemisphere. That might help us some. Now between our wind belts here, here's our trade winds, our westerlies, and our easterlies. We have little pockets. See the little pockets there where there's no little cell, no little wind belt? Those are the areas that we're talking about. The doldrums fall along the equator, the horse latitudes along 30 degrees north and south, and the subpolar lows along 60 degrees north and south. The two that you really want to remember, however, are the doldrums. They're a permanent low near the equator caused by the rising of the warm air. So the air's just going up and down. It's not blowing east or west. And then we have the horse latitudes, the permanent highs near the 30-degree latitudes caused by sinking cool air. And again, the air's just moving up and down. And the sailors used to have to throw, they would get caught there, no wind to blow their sails, and they would throw their horses over. And that's how it got the name horse latitudes. All right. Now, there's one other factor that affects the wind belts that we want to talk about. We've talked about latitude. That's where the air sinks at the certain latitudes, the 30-degree latitude and the 60-degree latitude. We talked about the Coriolis effect, which is the rotation of the Earth, making the wind seem to veer. Also, the cooling and heating of the continents is a factor that affects the prevailing wind patterns. Continents cool and heat more rapidly than the ocean. And if this is the United States and it's winter time, it's cool, creating a high pressure that's blowing the air away from it. See, the air is going away from the center of the continent. And if we follow the Coriolis effect, the air going away from the equator veers to the east. The air going toward the equator veers to the west, which puts us in a clockwise pattern. That means the air on the west coast is blowing this direction, while the air on the east coast is blowing this direction. Now, if it were summertime and it was hot over the continent, we would have a low pressure. As the air rose, the air would be sucked in, going towards the center of the continent. And here you can see if we follow that pattern, we're going to have a counterclockwise motion, and the air is going to be coming from the opposite directions once again. All right. Now, that's going to wrap up our lesson, and here's your assignment. You want to go ahead and read pages 40 through 43, do the section review, which is on page 45. I'm skipping a page on the ocean currents, activity 3, numbers 4 and 8. Where in the world was writing invented? It was invented in Sumer, which is modern-day Iraq. Before next time, see if you can find out where is one of the best-known deposits of asphalt.